First of all, thank you very much for the opportunity for me to be here. I am Suri, and I am making spectrographs. That's what I try to tell people in this conference. So, as an engineer, I implement science in terms of optics and mechanics and make things real. And we also need some electronics to control as well as the software for this controlling and analysis and data reduction. Right now, I'm based in Chile. We located in San Diego. We are part of the university in Católica, and we are located in this funny-looking building. We occupy one entire floor to be our labs and workshop and working space. Our center, it's called Center of Astroengineering. We build instruments from the ground base, and now we just have some satellite project going on. And this is my group. We are the optical infrared group. We have been building spectrographs since 2010, and today I will just focus on the high resolution, but we also have some multi-object spectrograph going on. For this very first instrument, we make push arrows as a prototype of our spectrographs, and we just commissioned videos this year, and this is the first slide of videos. I'm not sure that you can see, but and then we have Tardys. Each of these spectrographs, we bump up the spectral resolution, and we bump up the collecting area of the telescope, and we are also the consortium of HIRIS. We will do the software part for this one. So let me talk about TAO real quick. TAO is the University of Tokyo Atacama Observatory. It will have 6.5 meter IR optimized telescope in the summit of Surangkhana, and it will give quite good sight condition. We will have good seeing of about 0.7 arcsecond, and this is the transmittance. According to TAO, and to compare with Subaru here, we will be able to open a little bit of this window from 24 micron to 40 micron to the mid-infrared. And we can do some observation from the ground. The science motivation for this project is searching for exoplanet. We will use radio velocity method that Alan already told you about. And this is, the plot shows the confirmed planet detected with different methods, and radio velocity method is still one of the most important that you will need to combine the data with transit and characterize the density of your planet. And basically we just rely on, on this equation, the Doppler shift effects, and we derive from this equation to be our spectral resolution, and what we try to get is this kind of sinusoidal curve of the planetary system. For the technological motivation of this project, as you already heard in this conference, that there are a lot of space mission projects going on. What we are focusing on is TESS. TESS is going to launch next year, I believe, and then there will be a lot of target to be followed up. TESS expecting to detect something like 1,500 exoplanets, and in those, around 500 would be Earth-like, super Earth-like planets. So we are hoping to follow those targets as well from our instrument. And move you back to the ground base. These are the spectrographs existing, working in high resolution, near infrared. These are or in the northern hemisphere, but as you can see, there are so few in the southern hemisphere, and that's why it would be very fruitful to put Tardys in this southern hemisphere. Yeah, so let me bring you back to 2010. There was a big discussion of this exoplanet roadmap, what we're gonna do, how do we gonna characterize everything, and one solution that come out from this discussion is that we should move the target to cooler, lower mass star region. So that's why Tardys is focusing on more of the M stars type right now. And moreover, there is a study of Reiners et al. 2010. He was trying to calculate the spectral resolution that you would need to achieve and can search for this M-type star, which is well known of its relatively close habitable zone shown in green to compare with other type of the stars. There are a lot of M stars on the sky, but the reason that we don't really see them because this is the SED of M star. As you can see, it peaks at around 1 micron. So that's why most of the visible instrument cannot see them. This is what I use for my work. It's a program called CMAX. We basically model the ray propagation through all the optical elements in the system, and CMAX will give the analysis for our spectrograph. And at the moment, we will use 1K detector, and it also depends. If we go to the 2K, I will show you later how it would look like. The very first part of the spectrograph, we will apply what's so-called image slicer. Maybe you have heard it used in the multi-object spectrograph or IVU spectrograph. But this will be the very first work that used in the high-resolution spectrograph. It's basically the two small mirror putting in the right distance and right angle, and it will cut the image of the fiber into two halves and form the pseudo slit in front of your spectrograph. And this is how its spectrograph looks like. I guess you have already know it. We have entrance slit, we have collimator grating to disperse the light, we have camera to focus the image onto the detector. And my work will study the difference between the configuration of the setup. And we will essentially use this white pew configuration. We have two different types of grating. We use axial R6 and we use VPH grating as cross disperser. And this is basically the simulation of the 1K detector. It is called axialogram. It happens whenever you use axial grating in your spectrograph. And the text plotted here are the abundance that you might be able to see with this spectrograph. We have strontium, we have phosphorus, have sulfur, and some of the calcium triplet in the blue part. And in case of the 2K detector, we will be able to go to the wideband, and essentially we are now here in we are now in wideband, and we will be able to go a bit to the J band right here. And that you will see a lot more lines, especially the water that you can detect. The camera and the detector, this is the setup of our first design of optomechanical part of our spectrograph. We have input here, go to the collimating mirror, axial will be here, VPH grating, and the objective. We will cool down the last part of our spectrograph with the detector in the dual down to 80 Kelvin. And the wavelength calibration for the first generation, we will use uranium lamp. Normally in the optical spectrograph, people use thorium argon. And as you can see, uranium gives a lot more lines to calibrate your spectrum. So that's why we will use it for our first calibration. And later on, depending on the budget as well, we will try to go for ethanol. And this is the performance of our spectrograph so far. It's called spot diagram. It's essentially derived from CMAX program that I showed you before. This is the plot at the border of the detector, and this is the central wavelength. And the black circle means the iris, which means the best possible position that your optical system could achieve. And the scale bar here is 30 micron. And then I will just skip this technical part because it's a bit complicated, but basically we perform the tolerance analysis using CMAX as well. CMAX generate different files with the initial condition that we give to the CMAX and perform the sensitivity analysis using Monte Carlo. And we essentially will have this kind of distribution, and we choose the smallest merit function. Merit function is the function that allow you to measure the agreement of the data and the modeling fitting. And how to say it's good is the smaller the better, basically. Then we have this thermal analysis going on. We plug in the data from NASA that was studied with field silica that we used, and we found out that it will be defocused, so we have to shift the distance of our detector a little bit closer to the system, and everything will be okay again. So what's next? Right now, we are entering the optomechanical phase. So we try to fabricate, upgrading the mouse and everything. And I'm trying to do a bit of simulation for the exposure time calculator, taking into account of the atmospheric transmission and the throughput through all the system. This is actually very similar to the work from the spectrograph that I was working with called iGreen. iGreen was working in H and K band, and I just evolved the working wavelength to Y and J. And then, we try to make the web base out of this exposure time calculator, so it's a more user-friendly to the astronomers. And then we try to do a bit of the simulation. This would be part of the data analysis later. If you are working in the field, you might have heard of the program called EXOFIT, which uses MCMC, but we try to adjust a little bit. Instead of MCMC, we use Pi multinest. I wrote my code in Python mostly, but if we use Pi multinest, we will be based on more like nested sampling. And say we have this easy system of period of 10 days. And if you plug into our spectrograph simulation, you will see a little bit of the shifts through days that we try to simulate. And this is how it's gonna roughly look like in our detector. We will have dual fiber, the pseudo slit that I told you about, and the small dots are the calibration fiber. And now we are finalizing, well, we finished the design phase, and we are doing the optomechanics phase. And we will do the lab test next year, and the telescope itself should be finished in 2018, so we are the second generation instrument, so we hope for 2019, I think. And just a final remarks, this is what I got from that exoplanet community meeting in 2010, but I think it still applies for today. They said if you study habitable worlds, you cannot really avoid to do all that other stuff too. And it's not too early to start thinking about 2020 decadal survey to start making some technological investment. And I leave you with the summary for that. Thank you.